there are two files. Okay, the simulation files have been uploaded on Sakai, so you can actually access to that. Today in the morning, I uploaded it. So here we are gonna actually kind of simulate, the same case. Okay, so in this case, look at this one. There is a the green one is the particle energy, okay, or the wave energy, and then this purple well is essentially the potential, right? The finite square well. So in this case, the energy difference between the bottom of the well and the top of the well is 0.7 electron volt, okay? And then the particle energy is above the top of the well, right? That is essentially 0.2 electron volt. And then if you look at this wave function, this one basically shows you how the wave is traveling or how the wave is sent, okay? So this red and blue moving from left to the right, that is essentially the wave is being sent from the left, okay? And then, if you look at it, there is actually kind of the barrier or the energy difference, right? Energy difference here and the energy difference here. And at this boundary, the wave is essentially reflected back, right? That is essentially kind of this small magnitude here. And then some are transmitted here, and again, because this is where the energy bump is, and then there is also some reflection and then transmission, okay? So at the end, we can actually look at just what is reflected and what is transmitted. And then from this wave function, we can obtain also probability density, okay? And then this one shows you, how much reflection is expected, okay? This is a 0.4, 40%, and then transmission 60%, okay, 0.6, okay? So for this particular case, right, for this particle having energy of 0.2 electron volt, in this case, if you send the particle from left to the right, 40% will be reflected and then 60% transmitted, okay? So again, like this is unlike a bulk case, right? For bulk case, if you send the particle from left to the right, basically just above the barrier, 100% this particle will be transmitted, right? But for quantum mechanics, some are reflected and some are transmitted. And then as you can see, look at this one, now 0.2, and then if I increase, see what happens to transmission, right? I mean, now energy of particle 0.2, and then if I increase 0.25, then the transmission 67%, right? This is kind of increasing here. And then if I increase further, like now 0.5 electron volt, transmission becomes 92%. Okay, this is something kind of we can expect, right? And another thing we can actually look at here is that if I decrease the wall height, let me just change this one to the particle energy, let's say 0.02 electron volt, and then the wall height I'm going to change to 0.3, so like this one, okay? So the wall height is smaller, and then the particle energy is also just barely above the top of the well, okay? So in this case, transmission is 83%, okay? And then let me try to increase the particle energy, okay? So slowly increase. Now 0.02, 0.3, 91%, 0.4, 0.04, 96%, 0.05, 98%, and if I keep going, now 0.08 electron volt transmission is, like almost 100%, right? And at some point it's going to be 100%, and if I keep increasing, guess what happens to transmission? Did you see? Transmission now went from 100 to 99, and if I increase further, now transmission is going down, right? So this is essentially like what we expect, like from this plot, right? Basically, energy is being higher. At some point, transmission is going to increase, and it's going to hit 100%. If we increase the particle energy more, this is going to go down, and it will essentially go up and go down, go up. Okay, so in this case, you can again see this one. Now 96%, if I keep increasing, 94, and if I go higher, now it starts kind of going up, right? Now it's 95%, and then 96, 97, right? So basically, you know, with this simulation, you can kind of see this behavior, right? Basically, as we push energy higher for the particle, transmission, you know, is essentially oscillating, right? 100%, and then transmission going down, going up, and going down, okay? Okay, so so do you have any questions on this? Yes.
Why does it on the probability density graph?
So this
density
one,
graph, why does it go flat after it goes through? Is it still not a wave?
so this one is essentially kind of showing you. I mean, like this one, you don't really have to kind of look at this one. What I want you to really focus on is this reflection and then transmission. Because you know we sent a particle, and then we are kind of looking at how much is reflected and how much is transmitted. Okay, so yeah, rather than looking at this shape, yeah, look at this reflection and transmission coefficient. Okay. Okay, so any other questions here? Yes.
So the smaller waves on the left, are those what's reflected?
So yeah, so in the sense, if you really want to look at the kind of a wave behavior, look at this part.
Okay.
Yeah, so here, look at this one. This one is a reflection, and then this one is a transmit. Right? So in the sense, if I actually decrease this one further, for example, like you will see, I mean, this is still like, let me see, if I decrease. Yeah, so do you see actually kind of a reflection, the amplitude changes here for the second panel here? Like for example, if I decrease this one, reflection increases. So in here, you know, like this, for the second panel, reflection and then transmission. Okay. Yeah. And then that one is essentially captured here, like transmission coefficient and reflection coefficient. Okay. So you can kind of play around here, you know, and then, you know, I want to also show you other cases. Okay. For example, you know, this one has like a various kind of potential description. Okay. I mean, obviously for like let's look at this step function. Okay. So even for this step function, you can actually work on Schrödinger equation and get a solution, exact analytical solution. But you know, like I think that one is kind of beyond our course scope. So I'm gonna just kind of discuss this description, you know, this potential, just with the simulation result. Okay. So let us kind of look at this part. Okay. So we are essentially sending the particle from left to the right. Okay. And then now this particle energy is below this kind of cliff height, okay? So then when we send the particle from left to the right, you know, for bulk scale object, what did you expect? It's gonna hit the barrier and it's gonna stop there, right? You wouldn't expect any transmission, right? And then in this particular case, I mean, there is something you would expect, transmission being 0, right? You cannot transmit through it because this step function, this wall height is you know, infinitely long, okay? But one thing you can actually notice, or one thing kind of strange thing is essentially what is the probability density right after the wall. Okay, look at this one. So obviously it's not going to be transmitted, but if we send the particle just against the wall, you know, if it is just bulk scale object, it's not going to penetrate through the wall, right? I mean, that's a so obvious thing. But for this quantum mechanics kind of a concept on for like a nanoscale object, what is the probability right after the wall? It's non-zero, right? What does it mean? You know, like if you actually send like many electrons against the wall, there's still some chance that electron will be found after the wall. Okay, does that make sense? Because this one is essentially non-zero. Yes?
Would it be after the wall or in the wall? Because I thought the bucket was representing a wall of a thickness d, but this is this not?
This
So
is
this is like
this
a
is
wall
like
of infinite thickness. Is that
your wall with the infinite thickness. Yes.
So is it
And
saying
then
that there's a possibility that we'll find a particle that deep into the wall?
deep into the wall.
Okay,
Exactly.
but not on the other side of the wall. 'Cause it's-
Not outside the wall. Yeah. Because I mean, in this case, there's no other side, right? Because this wall is infinitely long, right? So that is essentially kind of an interesting part, right? I mean, but again, this one, the unit. Look at this. This is 1 nanometer, right? I mean, we are not talking about like after 1 meter we are going to find electron. Typically, we are going to find electrons at a very shallow depths, right? 0.5 nanometers in this case, kind of atomic scale. Okay. So and obviously, like in this case, if we increase the particle energy, what would you expect in terms of finding this electron in the wall, right? Yeah, something like that, right? So for example, if I increase this one, look at this one, right? If I increase further, now this one is kind of getting longer and longer, right? And then also at a particular location, probability increases, right? And it's something kind of you would expect, right? Because particle having higher energy, it'll actually kind of seep into, across the wall, right? So, and then that is kind of an interesting part. And then what if we send a particle above the wall height?
Some is reflected and some is transmitted.
Exactly, like it's like that, right? So for example, if we send a particle from left to the right, it actually sees this potential difference somehow, right? And then, for bulk scale, we don't care, right? If we send a particle above this one, I mean, nothing, it does nothing to do with this one, right? But, if we send a electron, like for this kind of under this potential difference, it actually sees the potential jump, and then some are reflected and some are transmitted. Okay, so in this case, transmission is 90%. Obviously, transmission is greater than reflection, but there is still some chance that this particle is reflected back. Okay. So if I actually kind of increase further, like you can see the transmission increases, right? And then obviously if I decrease the particle energy, the transmission decreases, but still, like more than half is essentially kind of transmitted. Okay. So this one is a kind of the case when we send the particle from left to the right. But what if we send the particle from right to left? Okay. So in this case, look at this, the direction of incoming wave from left to the right. But what if we send the particle from right to left? In this case, the particle is going to see the potential drop, right? So in this case, if I do this one, again, you can look at this one. We are sending the particle from right to left. So in this case, this is incoming wave, and then this is small waves are reflected, and then in this case, this is a transmitted wave. Okay. So in this case, it still sees the potential drop, okay, and then some are reflected, right? In this case, 10%, and then 90% will be transmitted through. Okay. So again, this one is a kind of a, like in striking contrast to bulk case, but like this is essentially the quantum mechanical nature. Okay, when you solve Schrödinger equation, this is exactly what you get, and actually, and even in experiments, it's kind of verified that this is the case. Okay. So basically, that is the kind of step function here, and let me see. Okay, barrier wall. And then if I come back to this barrier wall here, and I'm going to use, let me just kind of move the particle again, and just going back to particle direction, moving from left to the right. So what if I kind of make this potential wall height kind of flipped here? If I'm kind of flipping here, okay, and I'm sending particle from left to the right, okay, and then still this particle energy is higher than wall height, and then when there is a potential difference, okay, in this case here and also here, it sees the potential changes, and then some are reflected and some are transmitted. Okay, and then what if we send this particle just between these energies. Okay, the bottom of the wall height and then the top of the wall height. Okay, this is also kind of a very interesting observation here. If I decrease here, so I'm sending the particle. Okay, but in this case, the wall height or wall width is finite, right? It's not. It's no longer infinitely long, right? In this case, what happens is that, you know, I mean, if you look at it, very small wave is transmitted, right? The mostly kind of is reflected back, okay? But if I actually increase the particle energy, like look at this one, if I increase particle energy close to the top of the wall height, see what happens. You know, some sizable wave is transmitted, right? And then this is essentially transmission coefficient is 11%, okay? And then the reflection coefficient is, 89%. So what does this mean? You know, again, that is exactly like kind of this object, right? We are sending the particle from left to the right. If we actually send this particle 100 times, according to this plot, it tells us that 11 times we are gonna find the particles, you know, like the other side, and then, you know, like 89 electrons will be reflected back, stay there, right? That is essentially kind of what it tells us. And then this one is, again, you're not gonna see this case in bulk scale object. And then if you look at this one, basically, you know, this is essentially kind of where electron tunneling description kind of is met here. Like, have you guys heard about electron tunneling? That is essentially, you know, like that is a barrier, you know, like in bulk scale, you know, these objects cannot transmit through. But in this case, you know, like it actually kind of, you know, reflected and transmitted, and, you know, it kind of transmitting through the barrier, right? I mean, like classically, you know, impossible, but this electron can transmit through the barrier, and this kind of behavior is essentially described as electron tunneling, okay? So in this case, again, you know, the way to increase the transmission is, you know, basically increasing the energy of the particle, right, close to the top of the well. Then, you know, obviously you can see kind of higher transmission, okay? So that is essentially kind of how we can see, you know, in terms of, quantum mechanics, okay? So, so up to this point, do you have any questions here? Okay. So, you know, like there are several cases, you know, you can kind of play around here, you know, like basically there's a double barrier. You can also do that, you know, like as you kind of change this one, and then you can actually change this width, okay, and then you can make a kind of narrower one, okay, and then, you know, even though you are sending the particle, you know, there are multiple interfaces, and then because of that, there is a, you know, again, at every boundary you are going to have some reflection and transmission, but when we sum them up, eventually, you know, like this is essentially the result we got, okay? So transmission 26%, okay? So these are essentially kind of transmission or tunneling behavior, okay, for electrons, and you know, this one can be exactly described with a Schrödinger equation, okay? But again, you know, like this is step function or barrier. Well, you know, like we are not gonna work on Schrödinger equation, okay? But, you know, when you do that, you will get this result, okay? All right, okay, so